So I'd like to make a short or video about uh, estimation about how long it will take for the state to collapse. And I will use a metaphor from biology. This is a highly speculative video, so take it for what it is. But I thought it was very interesting too interesting to let go. So it came from observation of two things. The first thing is when state coercion fails, the scale is always enlarged. So if it doesn't work, scale it up is the idea, or if it doesn't work for the citizens at least. So people avoid coercion for tax havens or something. So coercion has to be extended to include these tax havens. And price controls over one good or service cause dislocations that call for more price controls in surrounding goods and services. So you see, state territory is always growing. We have the EU here now. We're soon going to have an EU president and an EU tax. And currencies are also imposed over ever larger groups of people. So violence always has to spread to surviving. It's basically the cartelization of government. So that's one observation. The second one is that if you look at life forms, then you see that more massive life forms have a longer life expectancy. So growing in size seems to be a survival strategy. Here you can see a picture with several life forms in it and their lifespans. And you can see that there's a trend line that shows that the bigger animals live longer. Now humans are a bit off the scale here. They're the highest dot in this graph. And humans should actually be only 25 years, every lifespan of 25 years, if you look at their mass. But yeah, we probably did a lot of stuff to lengthen our lifespans, and which other animals have not done. And I'd like to note that in ancient Egypt, the lifespan was indeed 25 years. Another thing to notice is also that over the last decades, people have been getting heavier, and I don't know how long this goes back, and their lifespan has been increasing. It does not mean you need to stuff yourself immediately to get very heavy to have a long life. I don't think it works like that. But it's something that is to be noted. So putting these two things together, I was wondering, could the growth of government be a survival strategy equivalent to what makes larger life forms live longer? In other words, is government a blob of biomass, a kind of superorganism with a lifespan to match its mass? And if so, what would this lifespan be determined on its mass? And it seems a bit far-fetched maybe, but apologists for coercion often say that government derives its power from the body of the people. And I always have to laugh a little bit because I imagine this enormous giant life form that if you look closer at it, you see that it is built out of all little individual humans, and it has a mouth that is all built of little humans, and the mouth speaks by all the humans moving. And it's all a bit of nonsense, of course, that it's often used that a group of people speaks as one, thinks as one, and acts as one. Only individuals act. But could it be that the person saying this, that he derives its power of the body of the people, is projecting in the sense that subconsciously he knows that he is part of a big organism called the state, and because he is unaware of it, he projects it onto other people. So that's an interesting thought. And now it is interesting also to look into what this whole business of longer lifespan comes from for bigger animals. And the theory behind it goes a bit like this. There's someone named Kleitner, and he invented what is now known as Kleitner's law. And that showed that the metabolic rate of an animal follows a power law with relation to its mass. So if you take its mass and you raise it to the power of 3/4, you get a proxy for its metabolic rate. You can see this in this picture for a number of animals, but it has recently found that this can be extended even all the way down to enzymes, and then you get a law holding over 27 orders of magnitude, and it is really astounding range, because if you look, for example, at physics and you say you want to calculate how a ball flies through the air, you need Newton's laws. But if you want to do calculations on something as big as a star or a black hole, then you need general relativity. And if you go to something as small as an atom, you need quantum mechanics to make accurate predictions. So that this holds over 27 orders of magnitude is quite remarkable. And how does this metabolic rate relate to the lifespan then? Well, the idea is that every cell has about the same amount of energy to burn over its lifespan. And if you take a slower burning rate, that means that the cell will live longer. So the large animal has a slower burning rate and therefore longer life. And you can see this in this graph of the 27 orders of magnitude. There's a second line on the right. By the way, the mammals are on the right upper corner. But if you take the cells of these mammals out of the mammals, and then you see that their burning rate goes up. And the idea behind that is that, the explanation behind it is that in a large animal the distribution of food and oxygen gets more difficult, and therefore its metabolic rate is slowed down, and therefore its lifespan is going up. And the reason for that, someone named Geoffrey West built a theoretical explanation behind that and said that if you start from two assumptions, and the first assumption is that the smallest distribution elements for food and energy are the same for all animals, and it is true that a capillary for a mouse is the same as that of an elephant. And the second assumption is that nature will find the most efficient network to distribute it. Then as an animal gets bigger, then it gets more difficult to find an optimal network to distribute energy and oxygen to the cells. And because of this, the cells burn slower, and that's what causing the 3/4 power law for the metabolic rate. And that causes the longer lifespan, because the cells have a fixed fixed number of amount of energy to burn. And indeed, when you take the cells out of the big mammals, then they start their burning rate goes up and their lifespan goes down. And this basically causes the whole big organism to slow down. So an elephant has a slower heartbeat, it has the respiratory system goes slower, so breath cycles go slower. And you could also rephrase it in saying that every life form has about 1.5 million heartbeats, every mammal at least. So a big life form, the heartbeat's slower, and it takes longer before the 1.5 billion heartbeats are finished. So that is an interesting way to look at it. And when Geoffrey West saw that this held over such a large order of magnitude, he came up with the idea to see if it would also extend to cities. And the metaphor of a city as an organism was already started by Aristotle. So it's not such a crazy idea. And he started to collect all kind of data, all cities all around the world, about the amount of roads, gas stations, total length of electrical cables. And it turns out that indeed infrastructure scales up with the same power law that is valid for biological organisms. So if you have twice the amount of people in a city, then you do not have twice the amount of gas stations, but only 2 to the power 0.77, almost 3/4. So it is 1.7 times the amount of gas stations. So for infrastructure, indeed, it seems to hold up, that it scales like a big organism. Now, he did find something else that is very strange, and I don't think he had a good explanation for it, and I don't have it either. And if you have a good idea, please leave it in the comment section.